I'm going to talk about Magnon spin currents in collinear antiferromagnets. I was asked by the organizers of the school to explicitly talk about Magnon spin currents. Turns out that like 10 years ago, I've been working on this subject, and actually I had forgotten it completely until very recently when new pieces have appeared that go under the name of altermagnetism, and uh, as well as new experiments have appeared which claim that they see some particular and interesting Magnon spin currents in collinear antiferromagnets. So I'm going to go over this experiment. So at the end of the talk, it's also a great pleasure to give a talk at Kourovka, where actually quantum magnetism was and is still thriving. And can say I'm an expert on quantum magnetism, and I hope my humble results are going to be appreciated here. Let's go. So my talk is embarrassingly simple, actually. There's no DFT, no Hubbard models, no correlations. I'm going to talk within uh, non-interacting picture. And so the plan of the talk is the following. And first, I'm going to talk about basics of antiferromagnetism. Then I'm going to review the classification of all antiferromagnets made by Slashinsky and Turov, introduce Dzyulashinsky invariance, and then, yes, go over this is what I call genuine antiferromagnets, ferromagnets, weak ferromagnets, and when talking about them, I'll be using the most simplest possible example, which actually conveys all necessary and important physics. Then I'll cover magnons and their definition of the spin density and the spin current, and go over the relevant responses of the magnet spin current to either temperature gradient or the external vector potential, effective vector potential for the magnons. So what I'll be meaning by antiferromagnets is the following. So there will be some lattice, let's say, of fermions at half filling, and the fermions are described by Hubbard model with a repulsive interaction. And at half filling, there's a nesting vector in the Fermi surface, and it drives the instability towards formation of the spin density wave, which is commensurate with the lattice well. In other words, it's in the antiferromagnetic state. The gap in the charge sector appears, and it's an insulator. So that's my antiferromagnet. I'll assume that the spins are collinear. So there's one sublattice and another sublattice. On one sublattice, there's a minus magnetization, minus spin, and another one is oppositely directed magnetization plus S. How I will be describing the interaction between spins is through the exchange Hamiltonian, which can be obtained from the Hubbard model by integrating out double occupancy states and obtaining the gap for the charge for the single particle spectrum for the single particle states, and reducing the system into spin degrees of freedom only, which reside on sides. The interaction constant, Heisenberg exchange interaction constant, is obtained from the Hubbard model in this way. It's a 4t square. So T is a hopping of fermions from one side to another, spin independent, and U is the Hubbard repulsion. So that's simple model I'll be keeping in mind when talking about antiferromagnet. There's no more anisotropies, etc. I will consider that the order is almost classical. Okay, so just plus S, minus S, that's it. What else will be important is the Zlashinsky-Mori interaction. How it appears. Okay, I'm going to switch now from the square lattice to honeycomb lattice, and how the Zlashinsky-Mori appears in the antiferromagnets is when there are, besides, in addition to regular tunneling, there's a spin-dependent tunneling of fermions from from side to side. Then when the Hubbard procedure is performed, then not just the regular hopping would define the exchange interaction, Heisenberg exchange interaction between uh, nearest neighboring spins, but also the spin orbit coupling lambda square here. In addition to the renormalization of the exchange interactions, there's going to appear what's called the Dzyaloshinsky-Mori interaction of that form. Data here is defined like that. If lambda is absent, spin orbit coupling is absent on the link, the spin orbit coupling, the Dzyaloshinsky-Mori interaction will vanish. Okay. How can I create such a Dzyaloshinsky-Mori on the link? For example, I have this kind of lattice, and this green atom is non-magnetic, but for example, it has a charge, and say it's positively charged, while the other two sides, red and blue, are negatively charged. So whenever so there's a possibility of having a dipole moment in the unit cell whenever the green atom is shifted from its symmetric position, which is in the center of the hexagon. And in this case, I can shift the position by external electric field applied to the plane of the sample of the system. Okay. Okay. Yeah, and again, one more time, I'll be considering the new order throughout the rest of the talk. New order is, again, it's compensated, fully compensated. Say one sublattice with plus s, another sublattice with minus s. There's no canting of the order. There's no frustration, etc., etc. Just almost classical order. It's only when I'll be talking about magnets I'll consider fluctuations about the order. So now I would like to classify all types of antiferromagnets. Actually, this type of classification was done by Turov. He followed Dzyaloshinsky. For that, one has to introduce two vectors. One is the new vector, L, which is the difference of the magnetization on the two sublattices. It's non-zero, and magnetization M. M is a pseudo vector, a real pseudo vector, and actually, it doesn't have to be related to the sum of the magnetization on the two sublattices. Okay, whenever the order is collinear, the magnetization is zero strictly. Okay, so what Dzyaloshinsky did in 1957 is that he said, okay, if a combination M alpha L beta is invariant under all symmetry transformation of the crystal, then it can appear in the free energy of the system. And it would mean that finite L in particular direction beta can generate a pseudo vector M pointing in direction alpha. This pseudo vector, one more time, can be due to counting of the nil vector. This was observed in iron garnet compounding by Borovik-Raman in 1957, and Dzyaloshinsky explained this with the help of his invariants. Said that okay, just this term, such a term is allowed in the system, and therefore there will be counting of the nil order, and that's what Borovik-Raman saw in the experiment. And then Turov, following the ideas of Dzyaloshinsky, he has classified all possible antiferromagnets for all symmetry classes. So here are two of his books. The classification is given here in this book, and there's the English translation published in 1965. And this is the also nice book, 1990. It doesn't have an English translation, unfortunately. However, all the effects of relevant and interesting effects of antiferromagnets are covered in this book. Okay, I would like to apply this classification scheme for my simple system, the most simplest one. This is the honeycomb lattice with this green side. And I claim that this particular combination of a green side is actually a genuine antiferromagnet in the sense that no finite magnetization or a real pseudo vector can get developed by any direction of the nil order. And the reason for that is because there are some symmetries. For example, there is a mirror symmetry. I'm sorry, but the x-axis is in this direction and y is here. So the reflection in this plane, following the time reversal, eliminates all possible invariants of this form. Now, it does appear that this kind of combination of a pi rotation and reflection in the XZ plane, and then so from here to here, I do the pi rotation about the center of the hexagon. So green atom went here, then I do the reflection, green atom goes back, and with all this transformation, sometimes the red are exchanged with the blue ones. So finally, I do the time reversal and restore the system as it was initially. So with M, the pseudo vector, which is in z direction, it actually also came back to its original form. So it does appear that such a symmetry allows for the MZLX type invariant, and it may appear that it's a weak ferromagnet. However, there is another symmetry, which is the reflection about the XY plane and time reversal. It completely eliminates the MZLX type invariance. So there's no pseudo vector for the reason of this symmetry. Also, in 2 dimensions, we expect to have a pseudo vector pointing only out of the plane. Now, if I lift the green atom slightly from the XY plane, then I will destroy the symmetry under the reflection, the XY plane, and time reversal. Therefore, I will allow for the MZLX type of invariant. Therefore, pseudo vector is going to be developed whenever the nil order is in x direction. So that's the weak ferromagnetism by Zlashinsky. Another definition of weak ferromagnetism is that, and necessary condition for weak ferromagnetism is that the 2 magnetic sublattices are necessarily have to be connected to each other by some symmetry operation. For example, here it was the YZ plane and time reversal. Now, realistic weak ferromagnets are those. Well, here's the list, many more. Some metallic, some insulating. And the claim by Turov, which I found in Turov's book, I believe, is that there are more weak ferromagnets in nature than the rest. That's how it goes. Now, an example of a weak ferromagnet can be given on the what's called the rutil lattice. Okay, so this is the configuration of the rutil unit cell. So the red and blue are magnetic sites with oppositely directed magnetization. Black ones are the ligands, oxygen, and yeah, they form this kind of structure. So a combination of rotation, pi over 2 rotation about the z-axis. So I just take this line and do the pi over 2 rotation, and then do a translation along this diagonal, and so I match the black sides. However, then I have to do the time reversal to flip the color of the sides. And if such a combination is present, then it will eliminate all possible Zlashinsky invariance with LZ direction. Other combinations allow for this kind of Zlashinsky invariance, MXLY and YLX. Actually, well, there's an insulating antiferromagnet coupled to F2. It has a lattice of rutil type, and its nil vector is pointing in the z direction. And there was an experiment in Kharkov in 1985. They observed exactly this symmetry, like what's now called as the D-wave symmetry or D-wave spin splitting of, say, of either fermions or magnons in the unit cell. These guys have already observed it, probably slightly indirectly, but they have observed it in 1995 by measuring the Faraday effect upon the transmission of electromagnetic wave in z direction whenever the parallel magnetic field parallel to the XY plane magnetic field is applied. And they saw exactly this dependence of the angle of the Faraday rotation. So in 1985, they already knew about the G-wave spin splitting you wish. Now, this was the weak ferromagnetism. Now, this is example of a ferromagnet. There are multiple of ways to have a ferromagnet. One explicit way is to have spins having different amplitudes. So this is a ferromagnet. I'm breaking the symmetry between the magnetic sublattices. Now I can also point the Neal vector in some random direction, which will break the symmetry of between the magnetic sublattices. However, in my opinion, this case is rather trivial because still the system will be described by Zylshinsky invariance consistent with the ferromagnetism, so it's a rather trivial case. However, one can also break the symmetry between the magnetic sublattices by ligands, by local non-magnetic environment. For example, in my simplest case, I'm putting the green atom over here. So clearly there's no symmetry between the blue and red, because blue sees green atom here from above, and the red ones, they see it from on the sides. So it's completely different configuration for the two magnetic sublattices. I can also place the green atom, say here, here. I have 5 more positions of the green atom when the system becomes ferromagnetic. Okay. Here I'm claiming that, whenever the atom is here, there's a special symmetry that does not connect the magnetic sublattices. However, it's a symmetry of the crystal, and it allows for the MZ-LZ type of Zylshinsky invariant. Therefore, whenever the Neal order is in the z direction, there will be a pseudo vector pointing also in z direction. So actually, in this particular case, you cannot come up with any counting of the Neal order to have because the Neal order is already in z direction. How can it count so that the finite magnetic moment is going to be in z direction? So this case is slightly different from conventional weak ferromagnets in this sense. I find it interesting, peculiar. Okay, so I'm concluding the classification by listing all possible antiferromagnets. So this is what I call genuine antiferromagnet it has an inversion and time reversal. It will never have the magnetization because of this symmetry. Now there are also genuine antiferromagnets, what I call the mirror symmetry, because it has the mirror symmetry and time reversal. There's a weak ferromagnet. Whenever I just take this green atom and lift it from the XY plane, then I'm going to break one of the symmetries, the reflection, the XY plane symmetry and time reversal, and it's going to be a weak ferromagnet, and there's also a ferromagnets in my case. Okay, so what about altermagnets that have recently appeared? In my opinion, altermagnets are here. So they are actually genuine antiferromagnets with zero net magnetization, no pseudo vector. There's indeed, one can come up with other lattices which won't have mirror but are rather pi/2 rotations, and time reversal symmetry is slightly more complicated than with just honeycomb. However, as I have shown, similar small difference of the green, small displacements of the green atom from its symmetric position from XY plane will make these altermagnets to be immediately behaving like weak ferromagnets. So that's my personal opinion, that altermagnets are not really, in any case, weak ferromagnets are the altermagnets. That's pretty much my opinion. Doesn't matter really. Okay, so this is the classification, and I'm going to, using those simple examples, 4 types of antiferromagnets. Actually, they have different physical properties, and I'm going to go over them next. So antiferromagnets are insulating. It seems that nothing will transport any heat or whatever. However, there are magnons. There are fluctuations about the order. And actually, the magnets are charged, and they can carry spin and heat. Turns out that I can create spin density of magnons or external fields and measure them. Or I can apply thermal gradients in the system and measure the heat flows of magnons, and I'm going to go over that now. But before I need to give some introduction of what magnons are and how to treat them theoretically. So there are magnons are fluctuations about the order. In order to analytically understand and describe magnons, it's convenient to go to Hausstein-Primakov spin representation. So there's a, for example, for red sublattice, there's a spin. So there's pointing in z direction. Okay, so there's a spin density, which is S minus A dagger A. A is a boson operator, and S plus is a raising operator. It creates a magnon, while S minus is a lowering operator, destroys the magnon. And I have yes, and then I write similar transformation for the P sublattice. It's slightly different because the spins on the other sublattice are reversed as compared to the first one. Therefore, I have to make some rotation first and then apply the Hausstein-Primakov transformation. And then what I do is I insert this representation into the Hamiltonian, exchange Hamiltonian. And among the other terms, I will obtain in the linear approximation such a Hamiltonian describing spectrum of magnons. So this is the basis: AK dagger, BK dagger, A minus, B minus. What's also peculiar is that there is a kind of similarity with the Bogoliubov-de Gennes Hamiltonians because it has the anomalous sector here and here. Here is the regular sector. 3 is just number of nearest neighbors. Okay, the Hamiltonian splits naturally into two blocks. So this is the first block, this, and that. And there's a second block. We can do them separately. Because they are bosons, the matrix that diagonalizes the Hamiltonian is para-unitary. It's here. So this is the matrix, which is made out of orthogonal and normalized spinors. Here, this and that. This is the matrix. This matrix diagonalizes the Hamiltonian. Here. These are the eigenvalues. Why it's para-unitary? Because there's the sigma-free matrix, which is 1 minus 1 on the diagonals. Here. Spinors, okay, there must be sigma-free. Spinors also obey this kind of normalization condition. Also, it's worth noticing that I'm no longer working in hyperbolic space. There's cosine hyperbolic, sine hyperbolic, etc. Expression is the following. It's square root of 9. It's 3 square minus dispersion modulus dispersion squared. Yeah, and the second block, well, it's similar to that. Similar to this. Yeah. Okay, so the second block can also be evaluated on the same footing. It's not that complicated. There's no reason to show it. Now I would like to discuss the spin density operator. So essentially, spin density is the difference of magnons on one sublattice is compared to the other. So it's given by this difference, AK dagger, AK minus BK dagger, BK. Why? Because SC is given to us by this combination S minus A dagger A, and the other one is by this. So if I sum them up, this is going to be subtracted, and the total spin of two sublattices is B dagger B say dagger A or the other side sign, doesn't matter. And how to write down the basis of Bocalibov Dijon type Hamiltonian is like this. Introduce this kind of matrix, commutes with the Hamiltonian, therefore the spin is good quantum number in the system. There are no sources or sinks in this evolution, and therefore whenever I write down the continuity equation for the spin density now, this is a spin operator, now it's a spin density, it's from the left and right I'm putting the spinors, and then whenever I do the continuity equation, I obtain a well-defined spin current, which is divergence. It's given to us that by divergence, and Js is the spin current. Here it is. This is the spin current. So as here is the spin density, sigma free appeared due to these commutation relations, and epsilon k is the dispersion here, this one. And the same for the second block. Now, the spin current, this is a density. It has to be related over the ground state or over the non-equilibrium state whenever the temperature gradients are applied. And yeah, we can then talk about, well, we can perform Cooper formulas, for example, obtain the expression for observed spin current in the system. Now I'm going to discuss 4 types of spin currents, 4 types of spin Magnon currents in the system. The first one is what I call is the Magnon equilibrium spin current. Magnon equilibrium spin current is similar to superconducting supercurrent. All right, so it's a response to the vector potential. Well, you might ask me, these are magnons, they are not charged. Where on earth I will find the vector potential for them? Well, it turns out that Dzyulashinsky-Moria can be an effective vector potential for magnons. It's not something I have found it by myself. It was relatively known. Now here's the example. So, for example, so in equilibrium, the spin current is having this expression. So it's group velocity times the extended distribution function, and minus, and I have to switch the blocks. So whenever the blocks have the same dispersion, and it's true if omega k equals to its minus k, and Hermitian conjugation. If it's true, then the spin current in equilibrium is going to be perfectly zero. So one block compensates the other. However, I can break this degeneracy by Dzyulashinsky-Moria interaction. Again, let's recall this simple lattice whereby external electric field, I can tune the position of the green atom. So for example, here I have placed the green atom here, and the green atom created Dzyulashinsky-Moria interaction along this bond here. And whenever I do the spin wave approximation, assume that it's still a magnetic order, still it's a new ordered state, and I do the spin wave analysis, then I will notice that some parts of the dispersion indeed have their momentum shifted in theta. Theta is the Dzyulashinsky-Moria parameter. Therefore, and I can do the same for magnetic case whenever the green atom is placed here. So minus here, this is the Dzyulashinsky-Moria on the bond of the arrow. And indeed, all parts of the dispersion have the momentum shifted in the Dzyulashinsky-Moria interaction. So therefore, this equilibrium spin current is not zero. Actually, if one plots the dispersion of magnons, and they're at the gamma point, they're going to have spin splitting. Here, one branch of magnons is split as compared to the other. And exactly this splitting will result in what I call the Magnon equilibrium spin current. It's going to be flowing to just apply electric field, and there's going to be spin current in the system. I'm not sure it's that easy to observe them because they are persistent. However, maybe one can do some kind of a ring experiment. For example, I can imagine a situation that I have my honeycomb lattice, my system, and I make a ring geometry out of the my honeycomb system. And then in the middle, there is an electrode with a plus charge, and on the outside, there are a number of electrodes with minus charge. So therefore, there is electric field penetrating the sample, and the electric field would shift this green atom and create appropriate or corresponding to the position of the green atom Dzyulinsky-Mori interaction. Dzyulinsky-Mori interaction creates the currents. The currents will flow. Here there are persistent currents. However, if I do the injection of equally polarized Magnon currents on the right shoulder and on the left shoulder, and then I collect them and interfere them together, then they must show interference as a function of electric field, external electric field created by plus and minus. This is the Aronov-Kosher experiment, actually. Aronov-Kosher effect. Also, what is interesting to notice is that if I estimate the value of this current at small temperatures is almost constant. I believe it's because of cotangent having 1 minus the 1 minus 2 was Einstein distribution functions, right? So it's exactly this one that gives me a constant, and it takes some temperature for the Bose distribution function to give some valuable, reasonable contribution to the integral. So it's only at temperatures equal to Sj, this Bose-Einstein distribution function gives some contribution, and here the current starts depending on the temperature in that way. Yes, the current is linear in the Dzyulinsky-Mori interaction at small temperatures. So this is plotted, the blue is plotted for minus 0.2, the yellow for minus 0.4. It's linear. Okay, enough for that. Now I'm going to, this is one current. So I would like to switch now into non-equilibrium situation when I'm having external temperature gradient applied to the system. And I'm going to talk about this recent experiment. But before that, I would like to introduce a system which I believe can easily explain the experiment, because the experimental system is rather maybe less intuitive. Okay, so this is my either weak ferromagnet or genuine ferromagnet, genuine antiferromagnet. And because, okay, so one role of the green atom was to create the Dzyulinsky-Mori interaction. This part, completely forget about the Dzyulinsky-Mori interaction. It's not relevant for the effect. However, what is relevant is the anisotropic in the magnetic sublattices, second nearest neighbor, exchange interaction given to us by here dashed line, this one. So within the why it's anisotropic, because we can assume that the green atom blocks the tunneling of fermions in the Hubbard, original Hubbard model through itself. So the green atom blocked this T, and maybe it didn't completely block T, but at least reduced the exchange coupling through the green atom. In my case, I completely disregard the exchange interaction through the green atom. So the only second nearest neighbor interaction is given to me by dashed lines. And it's different in the two magnetic sublattices. The difference, if I do the diagonalization Fourier transformation and obtain the dispersion, the difference is in this signs, plus and minus. The Dzyulinsky-Mori interaction is switched off, and at the gamma point, there's no difference between the red and blue, therefore spectrum is completely degenerate. However, at finite momentum, there's a Magnon spin splitting as a function of momentum. For example, here I have, say, plus, here plus or first block, this is the second block, or plus spin minus spin. And it's alternating in the Brillouin zone. So it's looking almost like D wave. However, if you zoom in, it's actually going to be mirror symmetric. It doesn't matter whether you can think that it's a D wave. Now, if you calculate, now you apply the temperature gradient to the plane of the system, and you want to study the response of the spin current, which we had defined before. The response, we want to calculate the spin current as a response to this external temperature gradient. Can apply the Lagrange formulas for that, etc., etc. Essentially, perform Cuba calculations, and one part of the spin current is given to us by this expression. This is the applied temperature gradient. It will necessarily come with 1 over temperature here. This is essentially this is a Green-Kubo formula. There are two Green's function. Integration over the frequencies would result in 1 over gamma. This is the heat current. This part is the heat current, and this is the spin current. Apart origination from the spin current. This is the distribution function, derivative of the distribution function over the energy. Again, if the spectrum of magnons is the same, then you can see that because of subtraction, the spin currents just absent in the system. However, if there is a spin splitting shown here, it's because of the second nearest neighbor interaction, then there's going to be spin current written like this here. So so there's going to be spin current along the x direction whenever I have the temperature gradient in y direction, and vice versa. They come with a plus sign, and it makes it different from regular Hall effect. For example, whenever so there's no Hall effect whenever the temperature gradient has such a configuration. Basically, it's applied along this diagonal. And whenever one of the components is strictly 0, then you might think you're getting the Hall response. However, it's not really the Hall response. And it does appear that whatever this new experiment have measured, and they measured the spin currents, magnons, and collinear weak ferromagnet, it does appear that it probably is this current. So here's the experiment. It is the LFO system. It's a weak ferromagnet. Space group 62, nil order in the x direction, a direction, and Turov. I took this from Turov's book, and here there's a Lashinsky invariant allowing for the magnetization in z direction. Actually, it's important for their experiments. Near temperature is 620, and the experiment is done at the price at 133 Kelvin, so it's above the room temperature. And so I don't want to dwell into the structure of this material, but what I can say is that there's a spin splitting of Magnon branches similar to what I've been showing here. So here there's a like almost D-wave spin splitting. They have the same spin splitting, whatever their direction is. So there's A direction and C direction. There's a spin splitting in B direction. There is no spin splitting. And what they do is they apply the temperature gradient in A direction here and measure the Hall voltage in the platinum through the inverse spin Hall effect. So even whenever there's excess of spin density in the platinum, metallic platinum, there will necessarily be Hall voltage, and they measure it. They can inverse the nil vector direction with the help of the canting. So they can apply external magnetic field And first of all, by polarizing all the magnetic moments, they also make the system with a monodomain. So pretty much a clear nil order. Then, by reversing the magnetic field, they can flip the direction of the nil vector. I find it fascinating. And they see it in experiments. So they have flipped the direction of the nil order, so this, and they see sign change of the hole voltage in the platinum. At least they saw it. Maybe they are applying in different direction, but okay, still the magnetic field, they can reverse the direction of the nil vector. Okay, so this is since I started talking about spin splitting, I have to mention who did what first. Okay, so that's that. So I guess I'll go on. And need to also mention that this kind of spin currents, they are dissipative. They required damping, just like in regular Cooper formula. It was first proposed in this 2019 by a Japanese group. And this is something that was observed experiment. Oh yeah, and they proved here in the experiment that if they apply the temperature gradient in the other direction, not A but B, in B direction, yeah, they showed here there is no spin splitting and there is no spin current perpendicular to the temperature gradient. Therefore, there's no hole voltage. I think they proved it. However, what they didn't do is they couldn't tune or they couldn't apply the temperature gradient along the C direction. It would be interesting to, for example, apply the temperature gradient along this direction and see no voltage drop, because this formula. So whenever the temperature gradient is along some symmetric axis, then the spin current is parallel with the temperature gradient, and no hole voltage is going to be observed. They didn't do that, so it's actually not a proof. However, it's a strong evidence that they have observed the magnon spin current due to the spin splitting of magnons in the brilliant zone. Okay. Strong evidence. Also, there is actually another effect. Well, this guy is called the effect Magnon altermagnet-driven Magnon spin splitter Nernst effect. Okay, so actually, I need to mention that it's not a genuine Magnon spin Nernst effect, because Nernst effect appears to be always perpendicular or transverse to the direction of the applied temperature gradient. For example, here. So instead of plus, there's going to be minus, just like in a regular Hall effect. Okay. And then no matter where you apply the temperature gradient, which direction you apply the temperature gradient to, you will always have the voltage drop in the platinum. Well, this effect is due to pericarvature and doesn't require dissipation. It would be nice if they measured, but they didn't see the traces of this current, because of they actually did some symmetry analysis as well and said that, well, maybe in this direction there's no Delachinsky-Morin interrupts. Yes, or yeah, I have to mention that the Berry curvature, which is responsible for the Magnon spin Nernst effect, is either due to the lattice or due to the Delachinsky-Morin interaction. But in any case, the Delachinsky-Morin is the driving force of the Magnon spin Nernst effect. Okay, so I'm almost finishing. I would like to now go over Magnon-thermal Hall effect in collinear antiferromagnets. So it's a little bit surprising that, okay, so you have a collinear antiferromagnet when the two magnetic sublattices completely compensate the overall spin. For example, like here, plus S and minus S, there's seemingly no magnetization in the system. Even in this case, there might be a Magnon-thermal Hall effect. Well, recall that Magnon-thermal Hall effect requires tilde vector in the system. Well, this pseudo vector is given by exactly this Zloshinsky invariant. So let's take the collinear ferromagnet. When the green atom is here, then the invariant is such, the pseudo vector is the z direction, whenever the nil vector is in the z direction. And when there's no spin splitting, the Magnon branches are split in momentum due to Zloshinsky-Mori interaction. And on top of that, I switch off the Zloshinsky-Mori interaction, and then the anisotropic second nearest neighbor exchange interaction is going to be giving me also some spin splitting in the Brillouin zone at finite wave vectors, but it's no longer d-wave symmetric or whatever else. It has no symmetry because the magnetic sublattices aren't connected to each other at all. And if you calculate, then again, the thermal hole is given by the barrier curvature. Is again non-dissipative effect. This is a thermal gradient. And if you just plug in the dispersion magnons here into this formula, calculate the barrier curvature, then indeed you prove that there's a finite thermal hole conductivity in the system. And both ingredients which result in the finite thermal hole effect are that are Zloshinsky-Mori interaction and the spin splitting. They both are important. They are coming from the broken symmetries that resulted in the this kind of invariant MZLZ. Remember, I needed to place the green atom here, break some symmetries, and while doing so, I have also created certain Zloshinsky-Mori interaction on the links, as well as the spin splitting, and both of them resulted in finite thermal hole effect eventually. So it's like that. Also, if I change the position of the green atom in the hexagon unit cell, then sign of the thermal hole is going to be alternating. Plus, minus, plus, minus, plus, minus. I can do it with electric field, for example. The same is with the weak ferromagnet. Now I'm taking the mirror symmetric, or whatever call it, antiferromagnet. I'm lifting the green atom from XY plane, eliminating mirror symmetry in XY plane time reversal. Doing so, I have also created certain Zloshinsky-Mori interaction, D1, D2, D3 on the links, here. And whenever the new vector, the new order is in X direction, only X projection of the Zloshinsky-Mori interaction are relevant for the spin waves. And yeah, as I again get the spectrum of magnons with Zloshinsky-Mori, D-wave type looking spin splitting. And yeah, I get the thermal hole effect whenever the consistent with the Zloshinsky invariant LX. So whenever the new vector is in X direction, I'll have a pseudo vector in MC direction, and this pseudo vector allows the system to have the thermal hole effect of magnons. That's it. That's pretty much it. So I think I won't be going through the conclusions. Thank you.
Look, I ask you, please, a simple thing. What experimental should do to measure spin current? What experiment should do to measure spin current? For example, if an experimenter wants to measure electric current by charges, it can take ampere meter, a current voltage source, apply voltage source, and measure current. The result will be resistance and prove that we really have. What should experimenter do to prove that in some substance spin current can flow?
I think there are two possibilities. Well, I think one way I have covered, right? So it's an inverse spin hole effect in the metal placed adjacently to the ferromagnetic system.
So experimenter should put very near to surface of antiferromagnet. Some metal.
Here, for example. So this film is a LFO. It's an
antiferromagnet.
This one.
Yes.
And on top of that, I'm placing a platinum wire.
Yes.
It's a metal, right?
Yes.
and it has a strong spin-orbit coupling. So whenever there's an excess of spin density in the platinum wire, there's going to be a voltage drop in the whole voltage drop in the platinum. And you
Voltage, we should measure voltage on the parts or the sides of this metal plate.
Exactly, yes.
And this will be the result of flow of spin current due to what? Due to thermally driven spin waves. Yes?
Yes.
Thank you very much.
I think another possibility would be make the Kerr rotation experiments. For example, on the boundary of the for example, apply the temperature gradient, there's a spin density flowing perpendicular directions, and then you can do some Kerr rotation measurement at the boundary of the sample and see that the signs at opposite boundaries are
Against by thermal gradient. So
Yeah,
all the current should be thermal gradient.
correct, because these are Magnons, there is no charge carriers. There's no any other way to excite outside it.
So are there any ways instead of thermal gradient to cause spin waves and to absorb this effect?
Well,
Are there
I have proposed another crazy way. Okay, so by applying external electric field
by electric field,
through the Lashinsky-Mori interaction,
by
directly you
can cause spin waves.
This is a crazy proposal, but yeah, why not? Yeah, apply electric field would be the Lashinsky-Mori interaction.
Okay,
And okay, yeah.
let me ask you concerning this analogy with supercurrent. If I understood you properly, you argue that the spin current is proportional to vector potential.
That's right, yes.
But because of the Gauss invariance, it cannot be just in such a way. You should add a certain gradient of phase. In superconductors, this is the phase of condensate. What quantity here plays the role of the phase of a certain condensate, whatever, yeah? Otherwise, it's just not Gauss invariant.
I think it would be the direction of the new order. Just I don't know actually, but maybe the direction. Maybe it's
complicated. Then this is okay.
Direction of the new order has angles. Maybe those angles will also appear here as a gradient of the phase, right? But I don't know the exact answer. Okay, so yeah.
Any other questions?
That's a good question. Yes. Right.
У меня не вопрос, а осторожное пожелание всё. По российской литературной традиции тепловой эффект Холла — это эффект Эттинггаузена или Нернста Эттинггаузена, в зависимости от того, кто там вдоль, градиент или температура. А то Холлу и так слишком много достается. Спиновый Холл, хотя это Дьяконов и Перель, и Аномальный Холл, хотя это Ликоин.
Вопрос?
Я сказал, что это замечание.
I completely agree, yeah.
У меня такой концептуальный вопрос. Когда делается бозонизация теории, то есть когда мы переходим из спинов к бозонам, результаты, вообще говоря, зависят от классического состояния, то есть над которым вы смотрите спиновые волны. Да? А в вашем случае это важно, то есть можно выбрать классический антиферромагнетик, либо canted антиферромагнетик, то есть
Важно. It's important, yes. For tensor, it's important because, say, certain direction of the new order will kind of excite certain Lashinsky-Mori interactions, for example. For some directions of the new order, some Lashinsky-Mori interactions are not important in the spin wave spectrum of Magnons, for example. And see, I was dealing with those invariants, Lashinsky invariants, right? And for certain direction, let me find an example. For example, here, so MZ, LZ. So for this particular direction of the Neal order, the system will have pseudo vector MZ, right? So if, say, I want to study magnons that will have the magnetic moment, pseudo vector, then I necessarily have to point the Neal vector in Z direction. If I point in somewhere other direction in LX, I I will have completely different effects that the magnets are going to show. So yeah, so it's important, I guess. Of course, just simple answer.
Yeah, thanks a lot for this nice talk. Actually, so I have one comment and one question. I'm from material science anyway, and so this green ion you showed here, and you're saying that it makes all these exchange paths inequivalent, and you're saying that typically this green ion it blocks exchange.
That's my option.
I completely agree with that. It makes inequivalent, but quite often, if you have some ion like this one closer to for instance, to blue one, right? So it typically provides some orbitals. So it not blocks quite often, but in fact it enhances quite often. It enhances the exchange direction. But this is absolutely correct. So it can be a very different way, and anyway, it makes inequivalent. It makes the exchange path
Just enhances, not blocks, but the other direction.
But this was a note if I can. So may I ask a short question still? Yeah. So I'm not quite sure whether I understood correctly. So this material, lutetium iron O3, so there is no inversion center, and it is altermagnet, as these Chinese guys claim, right? So there must be both exchange splitting, right? And because there is no inversion symmetry, there can be DMI. And what I missed actually, that you tried to discriminate, right? Or so which one is more important? The DMI or I missed something?
They claim that the DMI is not important in their case.
Not important. This is
they made some symmetry analysis and they said that, okay, it's not important.
It's not important.
Whatever
it's there,
was,
but not important.
What was important is the spin splitting.
Due to altermagnetism.
Yeah, and for this effect to occur, you don't need DMI at all. It's actually minus DMI will completely, the DMI parts, this current are going to vanish actually. But they're actually important in the other, in Nernst effect. And I'm not sure how they have discriminated and whether they have discriminated or differentiated between regular Magnon spin Nernst effect and whatever they have observed. So still an open question because they actually don't have solid evidence because they did not make the temperature gradient along the C direction.
Okay, we have time for a couple more questions.
A very short one. You draw analogy to the superconductivity. Is there any similarities to quantum Hall effect to topology?
Yes, not in this case, but I'm aware of studies of so-called topological magnons where there are edge states of magnons propagating opposite edges. Yeah, I'm aware, but it's not related to that because
Not directly. Thank you.
Okay, so the questions exhausted. So let's thank the speaker.
Thank you very much.